Okay, thanks for the introduction. Today I will talk about our work. Tell your graphics stack that the display is circular. Computer display has been mostly rectangular since 1975. The monochrome display is a rectangular. And years later, we have the RGB color display. In this picture, it's Apple II, and we will see that it's a rectangular. Time goes by, we have high-resolution desktop displays, and they are also rectangular. And we use the smartphones every day, and the display is also circular. Just the size is smaller than the computer display. However, recently, the wearable device changed the story. We will see the display is no longer the rectangular. They are circular. So in the past years, what happened is the display is moving from rectangular to circular. And we are embracing the non-rectangular displays. And we believe that the trend will continue. So we will see the hardware has changed. But what's the challenge to the software? Let me tell you the story first, then I'll give you some evidence. Let's look at the graphics stack. We know what the graphics stack draw is a rectangular area. But the display is circular. So only the circular area will be shown on the screen. And the shadow area in the four corners are invisible. In fact, they are discarded. So the system resources spent on these shadow areas has been wasted. You may be wondering whether what I said is true. First, let's look at a 20,000 foot view of the graphics stack. We know the graphics stack's role is translated to the translated app UI to the pixels on the screen. There are three stages. In the first stage, the CPU will do drawing. In the second stage, the GPU will do rendering. And in the last stage, the pixels final frame will be displayed on the screen. Let's look at it into each stage. On the top of the graphics stack is app UI. There are a lot of elements in each UI, and they are organized in a tree. Then, these elements will be translated to an intermediate representation, which is a display list, in fact. And then, the display list will be translated to the OpenGL commands. In the next stage, the GPU will load the texture to its memory, and then will execute shader to draw every pixels. And at the end of this stage, the GPU will produce the many surfaces. In the last stage, the display controller will blend many surfaces into a final frame. And then the final frame will be displayed on the display panel. In fact, this is a simplified graphics stack. The graphics stack is very complicated. As I believe only few people can understand it very well. And we cannot know every single detail too. But how could we know that the graphics stack is drawing a rectangular area, even the display is circular? Let's look into some evidence from the top layer to the bottom layer. First, let's look into the Android application. If we look at the graphic API, we will find everything is rectangular. All the elements in each UI is specified by the coordinates in the four corners. Let's move one layer lower. Let's look into the OpenGL commands. The OpenGL commands is the interface between the GPU and the CPU. If we look at the code, we will see all the textures are specified as a rectangular. Let's move one layer lower. Let's look into the Linux kernel driver. This code come from the is device tree code, come from the current Linux kernel for the LG Watch R. Let's look at this code. The panel name is LG OLED. This is the physical display shape is circular, but we can see the device tree specifies the display panel as a rectangular. So we can see the width and height. So by looking the evidence from different layers, from the application, from the OpenGL commands, or from the Linux kernel, we believe that the graphic stack is drawing a rectangle area. Also, the display is circular. So there are two top questions. Number one is, how many resources are wasted? Number two, how should existing graphic stack adapt? Let's start from the first question. In order to understand the resource waste intuitively, first we study how many UI elements are hidden or clipped at the display boundary. This is a game UI. We can see there are many elements in it. And we also can, in fact, none of them are hidden, but we will find 3 of them are being clipped by the display boundary. Then we studied how many CPU or GPU computation is be wasted. As I said, in the first stage, the CPU will do drawing, mainly including the shader compilation and shader linking and other commands. Compared with the texture uploading, we will see the drawing time and the rendering time are not very expensive. So there are not much CPU or GPU computation will be wasted on the invisible area. Next, we study how many traffic is wasted. We found about 10 megabytes per second memory traffic will be wasted on the second stage on the GPU operation. And there about 10 megabytes memory traffic will be wasted between the GPU and the display controller. And about 5 megabytes per second memory traffic will be wasted between the display controller and display panel. So for the first question, we find that few views are completely hidden, and not too much CPU and GPU computation is wasted, but there are much memory traffic is wasted. In order to understand this problem better, we have studied another 11 variable applications. So if you are interested in them, please check our paper. Now we have answers for the first question. Let's move to the second one. How should existing graphics stack adapt? For this question, the key point is which layer should be aware of the display shape. The graphics stack is very deep, and there are lots of layers. Let's look at from the solution space from the top to the bottom. On the top of the graphics stack, the first possible solution is we may overhaul the framework API. We may let the developer to be aware of the display shape. So all the elements can be confined in the circular areas. Definitely, there will be no waste, but you will design your UI very carefully. This is a big burden for you. And what's worse, this method is not possible because for different devices, you need to redesign your UIs for each of them because they have different shapes. The second possible solution is we may rewrite the UI libraries. Of course, this will free the developer's burden, but the problem is we know that the UI library has already been very complicated. So we have to change tens of thousands of code to let it be aware of the display shape. So this is a very hard task. It's not very, it's invisible. Look at bottom. There is previous works in ATC50, and they can reduce memory traffic between the display controller and display panel. But this method is incomplete because the memory because the resource waste above this layer has already been wasted. So looking at this method, they are infeasible or incomplete. So we propose a new solution on the OpenGL command layer. Our solution is OpenGL interception. The key point is we rewrite the shader program on the fly, just like the pseudocode. So our idea is easy. So if the pixels is in the circular areas, then we let the shader to render it. Otherwise, the pixels will not be rendered. So look at the picture. These pictures. On the left one is before rewriting shader. We will see all the pixels in the rectangular area has been rendered. The second one is after rewriting shader. We will see only the pixels in the circular areas are rendered. Does this work? Let's look at the evaluation part. Ideally, we will run the GPU profiler on the desktop, and then we run a benchmark on the variable on the watch. At the same time, we stream the profiling data from the watch. This is the ideal case. Our work is enabled by the Qualcomm's GPU profiler. This is a powerful profiler, and we can get the GPU usage information for each frame. But there's a problem. The novel wearable device will crash this tool. Maybe the device is too new, and the Arduino profiler cannot support them now. So our solution is we do emulation on Nexus file. We know Nexus file and LG Watch R have the similar SoCs. They have their GPU have the same architecture. They come from the same generation. The only difference is one is more powerful than the other. So let's look at the result. First, our method can reduce GPU memory read. In the experiment, we vary the background texture size from 64 by 64 to 512 by 512. And we can see our method can reduce about 20% GPU memory read if the texture size is 512 by 512. We know that the memory read is a bottleneck for modern GPU. Then, second, our method can reduce about GPU cycles. Look into the figures. If the texture size is small, our method will introduce some overhead because we rewrite the shader program. And this will need extra computation. However, as the textures become larger, this overhead can be offset by the benefit of saved memory traffic. So if the texture size is 512 by 512, our method can save about 11% of GPU cycles. Then we estimate the power saving. Based on the previous work in ATC5, 15, they reduce the memory between DRAM and the display about 7 megabytes per second, and they can save about 3 milliwatts power. If the power saving is roughly proportional to the reduced memory traffic, this is our assumption. So our method will save about 4 milliwatts during the second stage of the GPU operation. And our method will also save another about 6 milliwatts during the display stage. So let's summarize what I have done. For this work, there are two top questions. For the first question, we have proved that the graphics stack is wasting resources due to the screen shape. And we quantified the resource wasted on the LG Watch R. For the second question, we propose a pilot solution, but we interpose OpenGL commands and rewrite the shader program. And our method can save about 20% memory traffic and 11% GPU cycles. So let's look at outlook the future. We believe that the irregular display will become pervasive in the future. For example, one day when you walk into a shopping mall, you may see the smart mirror, which has a big irregular display. When you drive your car in the future, and you will see your dashboard has irregular displays. And when you wear the virtual reality helmet, you will also find the display is irregular. So we believe the irregular displays will become pervasive in the future, and the resource waste is likely higher because the screen is becoming larger. And this makes it compelling to adapt the graphic stack. In our work, we just interpose OpenGL command and we rewrite the shader program. We keeps the graphic stack, most parts of the graphic stack unchanged. So, however, if we want to solve this problem thoroughly in the future, we may think to redesign the graphic stack. Overall, our work is an interesting case as we are embracing the novel wearable or mobile devices. These devices have new form factors. And these new form factors drive us to rethinking some fundamental principles in system software design. Thank you.